Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to just try to help describe for you the relationships between position, velocity, and acceleration, and hopefully give you a decent enough understanding so that in my next video you'll have a better chance of understanding how position and velocity functions are derived from the acceleration of an object. So what we've got over on the right here, imagine we've got some sort of car, and at some time t equals 0, it's moving to the right. So I've drawn a velocity vector there in blue here, and I've given it a name, v sub o. And imagine that that velocity is increasing. Maybe the person's got his foot on the grass graph. So in that case, the car would be accelerating also to the right, and I drew that vector in green. Now, when you track a particle, typically the first thing you do is you define some sort of set of coordinates, which I've drawn here, x, y. So the location of the car would be described by x, which would basically be this, maybe this distance. Now, the position of the car is described by x, the velocity by this vector, and the acceleration by this vector. So there are three vector quantities: position, velocity, acceleration. And now we're going to talk about kind of graphically how they're related. So we're going to start with this picture right here. Now, acceleration can come in all different types of numerical flavors, if you will. I'm just going to kind of imagine kind of a generic acceleration here. It's not constant, but it is positive and to the right. So my acceleration graph might look something like this. And again, that's just one of any number of examples, but I wanted this video to be good pretty well no matter what. The area under this curve is effectively acceleration times time. So that gives a change in velocity. If I could somehow calculate the area under this curve, whether this was defined by just numbers or some sort of function, I'd be calculating the change in velocity for the car. And what that would allow me to do then is get my new velocity. This v of t is representing the velocity at this instant. And that's going to equal the initial velocity of the car, okay, which is, let me do this in blue, this distance, whoops, I said blue, this distance on the graph, and that's this vector here in my picture. If I take my initial velocity and I add my change in velocity, I'd have my new velocity. And that change in velocity, again, is coming from the area under this acceleration graph. All right, now let's look at this animal now. So this is a position graph. And at t equals 0, this distance on the graph would represent this position, the initial position of the car. Now, sometime later, my new position, that's what I'm calling x of t here, is equal to my starting position plus my change in position. And my change in position is equal to this area under this curve. Remember that the area under a velocity graph gives your delta x, or your change in position. So, in essence, these are the fundamentals that are going to allow us to write equations of motion to describe things like cars. Now, before we get to that, I want to talk a little bit about how these graphs are related going the other way. Remember that velocity is the rate that position changes. So in this case, that'd be delta x over delta t. And delta x over delta t, that's slope over on this graph. So that's how these graphs are related going this way. Your velocity is the slope of a position graph. And accelerations, delta v over delta t, that also is a slope. It's the slope of your velocity graph. So when we look at these three graphs, and again, let me just remind you, this was just a quick sketch. Here's an acceleration. I just put some curvature in it to denote it does not have to be constant. I tried to get the velocity graph at least reasonably well approximated according to this acceleration, but I don't claim it to be perfect. And the position graph probably would look kind of something like this. But the point of this video is not about the nitty-gritty little details of these curves. It's just generically how are they related. And going this way, they are related by area. Going this way, they are related by slope. So I think I'm going to leave that video, just end that right there. That's enough for now. This was meant to be just kind of a fundamental video, and I'll save the more specific ones for other videos, or the more specific examples for other videos. So have a great day.